All right, so last topic for convection is convection in enclosed spaces. So basically things like double pane windows, for example. You have two panes of glass, you have air on the inside, and that air on the inside is going to circulate around. And so we're going to have some convection from that. So again, kind of situation I was describing, have this enclosure in here, have heat coming in on one side. So what's going to happen basically, you have heat coming in, you'll end up with this side being the hot side. That hot side is going to heat up the air around it. So this air is going to kind of want to travel upwards. If this is the hot side, that means this is the cold side. Air is going to kind of want to travel downwards in that case. And then as you get this current going down on this side, going up on that side, eventually hits the top and bottom because, as I said, it's an enclosure. So there is actually borders on the top and bottom. Before, when you had a flat plate, it just kept on going up. Here it gets stuck and basically gets turned around, comes over to this side, then gets pushed down from the cold current, gets pushed over to this side, pushed up. So you end up having this recirculating flow coming through here in this situation. So this can actually be analyzed either analytically, a lot of math, empirically, the experiments that we usually do, or numerically, because this is a situation where it doesn't occur all that often. We're going to deal with it just the experimental way. That's the easiest way to deal with it. So just the empirical results that we've pretty much been dealing with for a lot of convection anyway. Important things about this are the Grashof number. So again, this Grashof number, G times beta, T1 minus T2. In this case, there's usually a length here. So length of the plate or diameter or whatever situation we're dealing with. In this case, we want a length scale appropriate to this particular situation. So my length scale and my Grashof number is usually the way of which the heat transfer is moving. So for the for this case, I want heat transfer going left and right. So the dimension that I want in this case is delta, not the L, because again, heat transfer going left and right. So it's the delta that I want for my Grashof number. Also for the Nusselt number is usually Hx over K or HL over K. Again, there's some length there in terms of which way the heat is flowing. Again, here, heat's flowing in this direction, so that's the dimension that I want. And like all other situations, what equation to use is really going to depend on the value of the Grashof number or the Rayleigh number, Grashof number times Prandtl number. At low values for the Grashof number, that means that fluid is moving really slowly. So the Grashof number is kind of like the Reynolds number. It tells me how fast things are going. Small Grashof number means very small currents. So as these things are moving, they're moving very, very, very slowly. Moving really slowly, then there's really not much convection going on. It's mostly conduction. So if you have a small enough Grashof number, pretty much ignore convection completely and just go with conduction. So in terms of these equations, assuming I have a large aspect ratio, so L is much bigger than delta. Again, that's kind of the situation in a double pane window. The height of the window is much bigger than the distance between the two panes of glass. Constant heat flux. This is my empirical relation for kind of medium-sized Grashof numbers, or Grashof times Prandtl number, the Rayleigh number. Again, below 10 to the fourth, not very much convection going on. So basically zero convection below 10 to the fourth. Once I get up this medium, between 10 to the fourth and 10 to the seventh, a few other parameters or conditions as well. This is my equation for Nusselt number, 0.42 times this Rayleigh number to the 1/4 power, Prandtl number to the 0.012 power, and this aspect ratio, length up and down over delta left and right to the -0.3 power. If I have higher values of the Rayleigh number, Grashof times Prandtl, between 10 to the 6th and 10 to the 9th, again, a few other conditions, I can use this equation, Nusselt number 0.046 times that value GRPR to the 1/3 power. A lot of times what we see for these situations is that the convection is actually expressed in terms of a effective thermal conductivity. So you kind of are transferring this convection into a conduction equation. The reason for that, again, is going back to what we said before about having small convection currents leads to just conduction. So you generally have conduction in here as well. This is a way to kind of compare the two heat transfer modes more effectively, because if I can set up a effective thermal conductivity, that's going to tell me essentially what the convection is doing. I can then compare that to the actual thermal conductivity K, and if one's much bigger than the other, I can ignore one of them. So the way we're going to do that is basically start off with our convection equation, HA times the delta T, T2 minus T1. Replace H by its usual coefficient, Nusselt number times K over delta. And then what I want to do is kind of transform this equation into the actual conduction equation. The conduction equation, remember, Q, Ka times the temperature difference over a distance. So this delta could be my distance, temperature difference, again, my temperature difference. I still have an area, that's fine. And then I want this K, it's going to be my K equivalent. That's pretty much everything left over on this side here. The stuff that's left over is basically just these two terms here, Nusselt number and actual conductivity K. So it's, in a sense, my effective conductivity Ke is just Nusselt number times the actual conductivity. And so Nusselt number, I can rearrange that to be Ke over K. And many other situations, so basically the only situation we dealt with so far is that case of kind of the dual pane window vertical enclosure with a small delta compared to L. There's many other things we can do. So we can have a horizontal temperature difference, so temperature difference on the top and bottom as opposed to left and right. We have inclined surfaces, so things going at an angle instead of straight up and down. Other geometries, so not just rectangles, but also spherical shells, cylindrical shells. So many other geometries and situations are described on pages 437 to 443. This is kind of like, again, what we did for all the other convection cases. There's many geometries, many conditions. Just find the right geometry, find the right condition, find the right equation for that, and then just go with the standard procedure. Most of these equations that you're going to find on those pages are expressed kind of in this form. So my Nusselt number is some equation Ke over K, some constant C, standard GRPR Rayleigh number to the n power, and then you'll have possibly some aspect ratio L over delta to some m power. And again, for whatever scenario we're dealing with, you can find values for Cm and n, and a formula possibly for Ke over K for that geometry, for those conditions in terms of value of a Rayleigh number or whatever else is going on. The first example of this, we have two 30 centimeter square vertical plates. So those, again, kind of like my windows, separated by a distance of 1.25 centimeters. Space between them is filled with water in this case, so not necessarily windows anymore. I have a constant heat flux imposed on the plates. So my temperature on one side is 38 degrees, temperature on the other side is 60 degrees, and want to find the heat transfer rate for this scenario. So as usual, first thing you want to do is find the film temperature. So film temperature in this case, not really the film temperature, because that's technically defined to be the free stream and the wall temperature. In this case, I can have two wall temperatures, but again, I want to find the average of those two values. So average of 38 and 60 gives me 49. And once I have that, I want to find all my fluid properties at that temperature. So table A6 for water at a temperature of 49 degrees Celsius gives me a density of 988 kilograms per cubic meter, a heat capacity of 4,181 joules per kilogram degree Celsius, viscosity 5.57 10 to the negative fourth. That'll be Newton second per meter squared. K value 0.642 watts per meter degree Celsius. Prandtl number 3.63. Any thermal coefficient of expansion 4.51 times 10 to the negative 4. That's 1 over kelvins. So plugging all that into my value for the Rayleigh number, GRPR, I have G beta rho squared Cp over mu K temperature difference, and again this delta cubes all those values, 9.81 for G, 4.51 times 10 to the negative fourth for beta, 988 squared for rho, 4,181 for Cp, 5.57 times 10 to the negative fourth for mu, and 0.642 for K. Temperature difference, 60 minus 38. And the space between my two sheets, 0.0125 decimeters. Cube that gives me a Rayleigh number of 2.17 times 10 to the 6th power. That is between 10 to the 4th and 10 to the 7th. So because of that, I can use this equation here, Nusselt number, 0.42, GR PR to the 1/4, PR to the 0.012, L over delta negative 0.3. These other conditions are satisfied as well. So Nusselt number 0.42, Rayleigh number was 2.17 times 10 to the 6th, take that to the 1/4 power. Prandtl number 3.63 to the 0.012 power. Then L, my length, height of these things was 30 centimeters. Delta between them was 1.25 centimeters. Don't need to worry about converting that because it's centimeters over centimeters, so it goes away anyway. So the negative 0.3 power gives me a Nusselt number of 6.31. And then finally, with that Nusselt number, I can find my Q value. So Q value equivalent to Nusselt number, which is K over K times the actual K, A times delta T over delta X. So again, this is kind of going back to the equivalent conduction equation, Ka delta T over delta X, with this additional factor in there, Ke over K, representing the Nusselt number. So 6.31, 0.642, area 0.3 squared, delta T 60 minus 38, and then again this delta X is 0.0125, gives me 642 watts for the heat transfer in that scenario. Now some of you may have noticed way back here on slide 5, when we had these equations for this scenario, these two vertical plates separated by a small distance. My first equation, the one we just used, 10 to the 4th and 10 to the 7th were my two boundaries on that, so I was at 2.16 times 10 to the 6th, so well within those bounds. You may have noticed this second equation for the higher values actually started at 10 to the 6th, so technically we could use that guy as well, because again, the value we had for GRPR was 2 times 10 to the 6th, so between those values as well. So previous case, we had 642 watts. Using the other equation, the second one, again, we're still within these bounds. So in that case, my Nusselt number, 0.046, Rayleigh number to the 1/3 power. So 0.046, 2.17 times 10 to the 6th to the 1/3 power gives me a Nusselt number of 5.96. Playing that back into the same equation. So now I have 5.96 my Nusselt number. Everything else is the same. Gives me a heat transfer of 606 watts. That's pretty close to what we had before, the 642. So you can see these two equations kind of overlap in that region between 10 to the 6th and 10 to the 7th. And in that case, either one is fine. Whichever one you use will give you fairly close answers to the other one. So whichever one you want, they both work. So again, as long as you use the right equation for the right scenario, sometimes you have a choice between two. In those cases, use whichever one you want. They both give you relatively close answers. So lastly, a little bit of a follow-up. I now want to change the scenario. Instead of dealing with this nice vertical rectangular enclosure, I want to change that to now a circular enclosure, so basically a cylinder coming in and out of the page. So length of 30 centimeters, outer diameter 10 centimeters, inner diameter 7.5, space between them filled with water, same constant heat flux condition, same average temperature, 38 for the inside cylinder, 60 for the outside cylinder, and again want to calculate the heat transfer rate. So luckily here, a lot of this is the same as before. So normally I'd want to find the film temperature, but that's the same as before, 49 degrees Celsius. Want to find my fluid properties, but then again, those are the same as before, same fluid, same temperature. Now when we get into finding the length scale or the Grashof number, on page 440, 441, when it talks about the scenario of the cylinders, it gives you this length scale to use. So before we use that value delta, here it wants you to use this length scale, kind of funny equation for it, but that's what everything else is based on, so we need to use it. So 2 times the natural log of the outer radius over the inner radius, that whole thing to the 4/3 power, divided by inner radius to the -3/5 plus outer radius to the -3/5, that whole thing to the 5/3 power. So plugging in all our numbers in this case, at a outer diameter of 10 centimeters, so radius is 5, inner of 7.5 centimeters, so again, radius is 3.75 in that case. So just plug all those numbers in. Gives me a length scale of 0.00515. This will be in meters, so that is an actual length in meters. Then I can plug that into my equation for GRPR, or Rayleigh number, in the same one as before, with all these values. Pretty much, again, the only thing here that changes is this length scale. So instead of being 1.25 centimeters, it's now this length scale, 5.15 millimeters essentially. Gives me a Rayleigh number of 1.52 times 10 to the 5th in this case. And in this case, again, I want to look up what equation to use for this scenario. On page 441, it says use this equation for KE over K, which again is a Nusselt number. So that's 0.386 Prandtl number over 0.861 plus Prandtl number, that whole thing to the 1/4 power, times your Rayleigh number to the 1/4 power. So plugging in the values we have, 0.386 as my coefficient, and on the inside here, 3.63 my Prandtl number on top, 0.861 plus Prandtl number on the bottom, that whole thing to the 1/4 power. Rayleigh number we had 1.52 times 10 to the 5th, again to the 1/4 power, gives me a Nusselt number of 7.23. And then again, plug this into our Q equation. Again here, using the Q equation for conduction. Conduction through a cylinder, remember. I have K times area times delta T over natural log of RO over RI. Again, that's for a cylinder. And then want to modify it with this Nusselt number, KE over K. So everything other than this KE over K is just conduction through a cylinder. KE over K, as I mentioned, was a Nusselt number, which we found, 7.23. K value, 0.642. 2 pi times a length of 0.3. Temperature difference, 60 minus 38. The natural log of outer radius of 5 centimeters over inner radius of 3.75 centimeters gives me a total heat transfer of 669 watts. So that is heat transfer through an enclosure, convective heat transfer through an enclosure. That is basically the last thing we need to learn about convection. So next week, we will be dealing with, actually not next week, technically next week is spring break. So basically 2 weeks, I'll resume posting these lectures. We'll have the conduction review, and then your test on convection happens the day after that. So might want to start studying for that. And I'll see you for the conduction review.